Hello, everyone. My name is Abhishek Mandal, and today I'll be presenting our work on measuring bias in multimodal models. So, as we have seen in the past couple of years, generative AI has made rapid progress, and they have been used to create many art or similar images. And as we go on, we will see more of such images in the internet, and they will be tracked and presented by search engines. All the images that we see in this presentation are AI generated. But we see this issue of bias in these generative models. So as you can see, for the text prompt and image of a data scientist, the generated images are mostly of men, whereas for the prompt and image of a flight attendant, you can see most of the images are of women. So we clearly see the issue of gender bias here. One of the main issues which I saw during my research is that in this field of fair, ethical, and trustworthy AI, there are different stakeholders. For example, we have people from the social sciences who have their own set of vocabulary and their own perspective and understanding. Then we have people from CS and engineering background who generally prefer a more technical approach of understanding these issues. Then further, we have people from law and policy, and they have their own understanding. So our main aim here is to present a metric that is understandable, easily understandable by all these different stakeholders. So let us take a scale. On these two sides, we have two concepts, A and B. They can be any concept. And then in the scale towards A, if this scale is from, say, 1 to -1, then if, towards A, the score will be towards 1. And if there is some bias towards B, it will be towards -1. So if we have a target which is biased towards A, it will have a positive value. And if it is biased towards B, it will have a negative value. So our main contribution here, which is the Multimodal Composite Association score, provides a simple metric which consists of a number and a sign. So the sign tells the bias, and the number gives us the magnitude of the bias. Now, if we replace A and B with two concepts such as gender, then on one side we have men, and on the other side we have women. And if we use the male gender to be represented by both images and text, so you can see we have images of men, and then a text such as he, him, man, boy, father, to represent the male gender. Similarly, we have images of women and text such as she, her, hers, woman, to represent the female gender. Now we have some targets which are real world concepts, for example, occupation, such as a CEO or a housekeeper. Now, if that concept of occupation has a male bias, then it will have a more positive score. And if it has a female bias, then it will have a negative score, and 0 if it is neutral. So the Multimodal Composite Association score has 4 constituent score. They are based on the cosine similarity, the difference in the cosine similarity between the attributes and the target. So the image association score measures the similarity difference between the target, such as the image of CEO here, and images of men and women. Then we have the image text prompt association score, which measures the similarity difference between the images of the gender and the prompt which was used to generate that image. So for example, an image of a chief executive officer was used to generate that image. Then we have image text attribute association score, which measures the similarity difference between the text attributes representing men and women and the target image. And finally, we have the text-text association score, which similarly measures the similarity difference between the prompt and the text attributes. Now, this is a very simplistic, high-level diagram of working of major text-to-image based models. So here we have the text input, which first goes into a text to embedding model, which in many cases is flipped, where the text is converted into intermediate representations. Then we have the diffusion process, which finally creates the image output. Now, each of these four constituent scores of MCAS measures bias in each of these four steps. The targets which we use to generate that our target images, we divided them into four categories, all of them representing some real world concept, and most of them have equal distribution based on traditional notions of gender. So for example, for the occupation category, traditionally CEO, engineer, doctor, and programmer have been male dominated, whereas beautician, housekeeper, secretary, and librarian female dominated. In sports, previous research has shown that outdoor sports such as baseball, rugby, they are more male dominated, especially in visual data sets, whereas badminton, gymnast, swimming, these are more represented by women. Similarly, for objects, we have cars, farm machinery, these are generally more associated with men, whereas food processor, hair dryer, they're more associated with women. So this is an example of the text prompt input that we gave and the output that we got. These are all generated by DALL-E, a generative model by OpenAI. For our results that we got, we see that for the category object, fishing rod, farm machinery, and car fixing, we see a presence of male bias in both DALL-E and Stable Diffusion, whereas food processor, hair dryer, and makeup kit, they have a female bias for both DALL-E and Stable Diffusion. For occupations, we see traditionally male-dominated occupations such as CEO, farmer, programmer having male bias for both DALL-E and Stable Diffusion, whereas beautician, nurse, and secretary, they have female bias in both the models, DALL-E and Stable Diffusion. For the scenes category, we see images with theodolite, snowboard, and lathe generally have a male bias, whereas dollhouse, reading, and shopping, they again have a female bias. For the sports category, we see outdoor sports such as cricket, rugby, and baseball. They have male bias, whereas indoor sports such as badminton, swimming, and gymnastics, they have a female bias. So in conclusion, we can say that MCAS can be used to uncover bias in large multimodal generative models. And we found the presence of gender bias in both DALL-E and Stable Diffusion. As this is a metric, this can be optimized. So machine learning engineers and production teams can use this metric to debias their models. It is comprehensive and easy to understand, and it can also be scaled up or down depending on the needs. And the individual components of MCAS can also be used independently. And this is not just for gender bias, but it can be used for any other kind of stereotypical bias. Thank you.